which is, of course, the evaluation of forensic evidence. Then I'm going to show you the definition of likelihood ratio and show why it works. And finally, in the last part, I'm going to talk about an application of likelihood ratio to an identification technique. Well, whenever we are dealing with forensic evidence, there is the element of uncertainty to be accounted for. This forces us to reason in terms of probabilities. And indeed, forensic practitioners are usually asked to provide a probability to their findings. I want to specify that when I say probability, I don't mean a subjective degree of confidence, but something more rooted in data. So there will be a probability in the frequency sense, which is that the probability of something is the long-run frequency of occurrence. So basically, you need to try it many times and to record how many times it works. This is something that in many fields has been done very well. Some nice examples are DNA profiling and fingerprints. And sometimes this experiment has not been done. So the assessment is often done just according to the experience of the forensic practitioner. Of course, probability is not an easy topic, and indeed in real life and also in the law, the misunderstanding and misuses of probability are frequent. To try to combat this issue, in 2015, the European Network of Forensic Science Institutes has published some guidelines for evaluative reporting, which means the reporting of assessment of evidence. And one thing that stood out in this guideline is the recommendation of the use of likelihood ratio. So let's have a look at the motivation behind the guideline. According to the MC, there is a general lack of common criteria for assessing and reporting scientific evidence. This has an effect on possible miscarriage of justice because the same findings could be expressed and delivered in different ways, and those messages could convey very different conclusions, and that could bias the judge or the jury in a way or on another. So what they want is to get a standardized way to deliver the assessment of scientific findings. So what they propose is, well, there are several requirements. The first requirement I'm going to discuss is the use of alternative propositions. That means that whenever we assess the probability of an evidence, we need to consider two competing accounts. Let me give you an example. Say that bloodstain has been recovered. We need to specify two propositions, and those two propositions could be that the bloodstain came from the defendant, and the alternative proposition is that the bloodstain came from another unknown individual. These propositions are usually called the prosecution proposition and the defense proposition. Okay, this might look pretty obvious, and I want to highlight why this is important. So I give you a very edge or extreme example. Say that the evidence is that it's just a photo that shows that the perpetrator had a black phone. The phone is very blurry, and we cannot see any detail of this phone beside the color. And it so happens that the defendant has also a black phone. One could argue that the phone of the defendant fits perfectly the evidence. We can even say that the probability is 100%. Which is a true statement, but it's also misleading because it overplays the significance of this finding. By considering the alternative proposition, which is that the phone belonged to somebody else, we are forced to evaluate the probability that the phone of somebody else's will match the photo, and this probability is going to be high because black phones are very common. and any phone will match a blurry photo. So this will show that the weight of this kind of evidence is very low. A related example could be the following. There is the shoe belonging to the defendant clearly matches a partial footwear mark found on the crime scene. Now, by enforcing the two propositions, we need to ask ourselves, how distinctive is this mark? Maybe a lot of shoes will produce the same partial mark, and we need to quantify how likely it is that to happen, to have a complete picture about how significant is this kind of evidence. So the second important recommendation of the guideline is the use of likelihood ratio. So this is how the likelihood ratio is explained in the guideline. You need to compute the probability of the evidence given the prosecution proposition, so that the defendant is guilty. Then you need to compute the probability of the evidence given the defense proposition. And finally, take the ratio of the two probabilities. So if we write down this statement, for example, we could get that the likelihood ratio of 1,000 means that the findings are 1,000 times more probable if the defendant is the perpetrator than if the perpetrator is somebody else. Now, if you ask me, this statement is not very clear. It's pretty unintuitive and it's complex. So in my mind, I will try to simplify it. And when you do that, what you get is always wrong. I've written down the common example, like for instance, this statement does not mean that the defendant is 1,000 times more likely to be guilty than innocent. And it doesn't mean that the probability of the defendant being innocent is 1 out of 1,000. None of that. The problem with reading this sentence is that it doesn't have a clear meaning. So to understand why the likelihood ratio is actually a good measure, we need, unfortunately, to use a little bit of probability theory. So we came to the second part of my talk. And in order to not leave anybody behind, I wanted to put a small review of probability. So let's start with conditional probability. The conditional probability of A given B is the probability that the event A occurs, given that the event B has already happened. So let's look at a small easy example. If I throw a 6-face die, the probability of getting a 3 is 1 out of 6. But the probability of getting a 3 if somebody else has already looked at the result and told me that the result is even is going to be 0, because 3 is odd. On the other hand, if I know that the result is odd, the probability that my result is 3 is 1 out of 3. And an example is that if the result is 3, the probability that the result is odd is clearly 100% because 3 is odd. So hopefully this will give you an idea. Let me give you another example. And one property of the conditional probability is that it has a sort of direction. So the probability of A given B is not the same as the probability of B given A. So here we have hopefully an intuitive example. What is the probability of needing hospitalization if I've been shot? I will say that this probability is very high because being shot is a serious condition. On the other hand, if I'm at the hospital, the probability that I've been shot is quite low because there are a lot of reasons to go to the hospital besides being shot. That would be the idea. And another topic that may sound familiar is Bayes' rule, which is a theorem that helps us whenever we have a conditional probability in the form of A given B, and we want to know the opposite probability, which is going to be B given A, right? that's just a reference. We will use it, but you don't really need to remember it. Right, so another concept is the one of odds. Odds is a way to talk about probability that is more related with gambling. And it's pretty simple, actually. The odds of an event is simply the ratio between the probability of this event and the opposite event. So if I say that an event has an odd of 4, I'm saying that A is 4 times more likely to occur than the opposite event. So, of course, from the odds, you can calculate the probability. So if the odds are 4, we are talking about an event that has a 80% probability. So the takeaway lesson from this small part is just that probability and odds are different, but they represent the same information in different forms. Okay, let's go back to our trial. Let's call E our evidence, and let's call G the event that the defendant is guilty. Then the probability of the defendant being guilty given the evidence is going to be P of G given A in the form of conditional probabilities. So again, it's the probability of the defendant being guilty when we take into account the evidence. If we just write P of G, that is going to be the probability of the defendant being guilty, but without considering the evidence. Okay, so it's key to understand the difference between those two. I'm talking about the same event, but in one case I'm considering the evidence, and in the other I don't. Okay, now, using Bayes' rule, we can prove the following. I spell it out for you, so we don't need to really use the symbols, but what we are looking at is that the odds of the defendant being guilty given the evidence equals this ratio multiplied by the odds of the defendant being guilty without considering the evidence. So I'm going to put this formula on the top of the page. So what am I saying is that this ratio, this quantity, represents the change in the odds before and after. So the odds, before I consider the evidence, the odds are a certain way, and then to update or to change the odds and consider the evidence, I multiply by this ratio. And of course, this ratio is the likelihood ratio, as you might have guessed. So this is why the likelihood ratio represents semantically the weight of the evidence, because when the evidence enters the field, when the evidence is taken into account, the odds change by multiplying them by the likelihood ratio. So before we read the definition of the likelihood ratio, that wasn't really clear, but if we look at this formula, we see, hopefully in a more clear way, what is the role of the likelihood ratio and why the MC recommended it to represent this idea. Okay, now that we have had a look at the formula, we can try to understand how the likelihood ratio works. So the important formula is, again, the one on the left, and we can see that if the likelihood ratio is bigger than 1, then the evidence supports the prosecution statement. Why? Because when we consider the evidence, the odds of the defendant being guilty gets bigger because they get multiplied by a number that is bigger than 1. On the other hand, if the likelihood ratio is lower than 1, then the opposite happens. So the odds get multiplied by numbers more than 1, so they become smaller. And finally, if the likelihood ratio is roughly 1, then the evidence doesn't really change anything. Okay, so that's the interpretation. The bigger the likelihood ratio, the more the support for the prosecution, and the smaller the likelihood ratio, the bigger the support for the defense statement. So next, I'm gonna show you how to compute the likelihood ratio in a couple of examples. So let me remind you of the two parts of this formula. We have the probability of the evidence given that the defendant is guilty, and the probability of the evidence given that the defendant is not guilty, so the evidence was left by somebody else. Let's have a look at an example. Okay, so say that a blood stain had been recovered at the crime scene, and the perpetrator blood type has been determined to be AB+. And it just so happens that the defendant blood type is also AB+. So now, let's try to compute the likelihood ratio. So if the defendant is the perpetrator, any blood stain left by the perpetrator is going to be AB+. So the compatibility between the perpetrator and the defendant is perfect, is 100%. This is the first part of the formula. Now, let's consider the defense proposition. If the perpetrator is somebody else, an unrelated individual, the probability of his blood type being AB+ is just, well, the frequency of the AB+ blood type in the general population. So in this case, I've written down this frequency for, I think it's Spanish population, but don't quote me on that. So we can calculate the probability of the evidence being produced by somebody else, which is just the probability of AB+ blood type, which is 2.5%. So finally, we can compute our first likelihood ratio value, and it's just the ratio of those two values. So 100% over 2.5%, which gave us 40. So by the previous slide, we can say that the evidence provides some limited support for the prosecution. And as a comment, we can see why. Because the match in the blood type of the defendant with the evidence is perfect, but the blood type AB+ is relatively common in the population, so it's not very distinctive. If we had another blood type in our simulated crime, we could have got different results. For instance, if we had the AB- blood type, which is much less common, the likelihood ratio would have been 200, which is quite bigger. And if the blood type would have been A+, which is very common, the likelihood ratio would have been much smaller, because such a common event would not have supported a conviction of a specific individual. Okay, so in the previous example, we didn't have any possibility of uncertainty or error regarding the test. So I created another example, which is a little more complex. Let's say that the perpetrator has been recorded by a security camera. The image is very dark. You only see a shadow for a brief moment, but this allowed the police to estimate the height of the perpetrator, which has been determined to be 183 centimeters. Okay? So this height estimation technique is not completely accurate, but the police have run some experiment in a similar situation, and they have determined what kind of error you can get. And they gave us this table, which says that in all the cases, you get an error of up to 3 centimeters, and in 80% of the cases, the error is below 2 centimeters, and so on. And let's assume that the defendant is 181 centimeters tall. So there is a difference with the estimation of the police. But if we take into account the possible error of 2 centimeters, they became compatible, and we even know how compatible they are. The probability is 80%, right? So we already calculated the first part of the likelihood ratio. Now, we need to know what is the probability that a random person has his height estimated as 183 centimeters. So First, we look at statistics about the height of the population, and we can see those are the values around 183. And second, we need to consider the possible error. So if the estimation is 183, maybe the true height is 181 and the police made a 2-centimeter error, or maybe the true height is 182 and the estimation was off by 1 centimeter, or maybe the estimation was not off and the true height is 183, and so on. So finally, we get our result of 7%. And with this, we can compute the likelihood ratio, which now becomes 80% over 7%, which gave us 11. So I would like to point out that if we didn't consider the error in the estimation, on the one hand, we would have excluded our defendant because the height didn't match. And on the other, we would have overestimated the significance of the evidence, because instead of considering that only the 3% of the population match the evidence, we are saying that this value is 7%, so almost twice as much. Okay, now that we have seen how likelihood ratio works with some example, we can try to figure out how it works in general and interpret the formula. So let me give you my opinion. My opinion is that the first term represents the degree of matching between the evidence and the defendant, while the second one represents, we could say, the matching between the evidence and the general population, or you can also say that it tells you how distinctive is the evidence. And that's a good point, because if you are expecting to get a very high likelihood ratio value, because you think the evidence is going to be very significant, you should consider that, well, both parts of the formula. So the matching between the defendant and the evidence should be good, but more importantly, the distinctiveness of the evidence should be very high. Otherwise, you will never get a big number from this formula. That's the bottom line I wanted to point out. Like in example with the blood types, if we are dealing with a common blood type, we will never get a very high weight for this kind of evidence. One of the elements that I've mentioned, but we didn't really went deep about it, is the population. According to the MC guideline, a key aspect of applying likelihood ratio is considering the relevant population, which means the population that matches the available information about the case. Such population is also called cohort. On the right side, you can see an example where the population was not chosen wisely, and as a result, it's very easy to identify the incorrect person. But if we want a more serious example, we can look at this one, where it says, consider an isolated town in which a rape has been committed. There are 10,000 men of age in this town, but only 200 of them work at an underground mine. It has been determined that traces of minerals has been found at the crime scene. So the police thinks that the perpetrator must be a mine worker. So in this case, whatever analysis we run after knowing this, we need to consider as a population only the mine workers, not all the men in town. If we don't do that, whatever evidence we find is going to be diluted in a much bigger population, which is very likely to reduce the effectiveness or the weight of the evidence. Okay, now if we go back to our statement, our definition, the first definition that we read about likelihood ratio with the same number, maybe now we can understand what it actually means. I've written down the wrong interpretations, but if we look at the formula, we can see that the odds of the defendant being guilty, considering the evidence, are just the likelihood ratio multiplied by the odds of the defendant being guilty without considering the evidence. So having a likelihood ratio of 1,000 means that by considering the evidence, the odds of the defendant being guilty increases by 1,000 times. Okay, this is the complete interpretation. We should not read more into it. In particular, one can think that given that we are multiplying a number by 1,000, this number is going to be high. But this is not the case because we don't know how big are the odds of the defendant being guilty without considering the evidence. This number could be very, very small or even zero. So we cannot talk about the result of an operation by just knowing one of the factors, right? Okay, so my conclusion about the likelihood ratio are the following. I think it works very well because semantically it quantifies perfectly the weight of an evidence. So in this case, this is a very good choice from the MFC. It has been endorsed by the MFC, which is an important thing, and it's a first step towards standardization. It can be computed in practice. I gave you some simple examples, but later we will see application more closer to the real world. And finally, even if I didn't touch about this topic, it's easy to integrate multiple evidences when you are using the likelihood ratio, right? So this is another important advantage. And as an issue, I mentioned that the direct interpretation of the formula is very unintuitive and it can easily be misunderstood, although a lot of things in probability theory are easy to misunderstand. So maybe this is not such a big flaw. All right. So now I'm going to show you how to apply likelihood ratio to one identification technique, which is craniofacial superimposition. A short recap about craniofacial superimposition. This is a technique for personal identification or exclusion. And the process involves comparing a recovered skull with a photograph of a candidate before his death, so ante-mortem. In this process, well, the skull is overlapped on top of the ante-mortem picture in a way that the skull has the same pose of the face, and also the condition in which the photo has been taken, such as the kind of camera, the kind of lens, the distance to the subject, etc., are also taken into account. And once we have created this overlay between the face and the skull, an analyst can evaluate the anatomical consistency between the two and possibly make a decision in terms of identification or exclusion. Of course, taking into account all the other information available about the case. So traditionally, skull face overlay has been carried out in a number of ways. For instance, at the very beginning, that way was taking pictures of the physical skull, and the pose of the skull was adjusted between shots until the photo looked more or less like the photo of the face. Then this technique was replaced through the use of a video camera that allowed the operator to look at the final image while adjusting the position of the skull. And in more recent years, instead of manipulating the physical skull, an operator will use a 3D model of that skull inside a computer using a 3D modeling software. Anyway, creating an overlay this way can be very tedious and time-consuming, and the end result can be quite subjective, which is something that motivated. On one end, the development of our software Skeleton ID as a specific software to facilitate all the tasks in the superimposition process, and also as a researcher, it motivated an effort towards the automatization of skull face overlay using artificial intelligence. So let me tell you about this process. The key difference of the automatic version is that in this case, we are employing a set of corresponding anatomical landmarks that are located on both the face in the photo and the 3D skull. And then the computer uses this landmark to overlap. So the guiding criteria is that the landmarks should overlap as much as possible, but also we need to take into account that in the anatomy of the face, the landmarks on the skull are separated from the landmark of the face by the soft tissue that makes the face. Right, so once we have solved skull face overlay automatically, the next step will be to perform the whole identification or exclusion process also automatically. However, at this time, it seems unlikely that a computer method could easily perform the complex evaluation of anatomical criteria that is required and that is usually done by a trained professional. Therefore, we are aiming, well, we aim actually at a simpler problem, which is ranking. So instead of detecting the perfect candidate for a certain photograph, we just want to sort all the candidates according to quality in a way that the most promising candidates are put first. Therefore, the analyst just need to review a small number of the best candidates instead of all of them, which is going to lead to a lot of to big saves in time. So to explain things more precisely, we need to consider a close identification scenario where, due to the circumstances, it has been determined that we have just one photo of a candidate, and we are sure that this candidate is going to match with one of 3 recovered skulls. So the intuition behind our method is that when we consider the correct skull, so the skull of the candidate, the overlap between the landmarks of the skull and of the correct photo is going to be perfect or very good, right? Because there is some uncertainty due to the soft tissue, but we expect the overlap to be very well. On the other hand, when we are considering the wrong candidate, so a different person, we expect the landmarks not to overlap as well, right? So our idea was that to consider how well the landmarks overlap technically by measuring the distance between the position of one landmark and the other. So we measure this distance and we use it as a score, as a quality measure. And finally, once we have a score, we can just order the results according to the score. So I'm talking about something like this. On the left, you see a very good superimposition. And we calculated his score, which is 11.01, and this is the best result. So we put it in the first position of the ranking. Then we move to another overlap, which gave us a slightly worse score value. So we put this as our second entry in the ranking, and so on. So how do we know that this ranking is effective? Well, we perform a large experimental study, which involved 78 skulls and 78 subjects. We took 10 random photo of each subject. So in total, we performed over 60,000 comparisons. And what we found is that on average, if we look in the ranking for the correct candidate, ideally this should be first all the time. It's not, but the correct candidate on average, it appears at the position 3.4. So between the third and the fourth position out of 78. That means that on average, the forensic analyst, instead of having to look to all these 78 superimposition to find the correct one, he just need to look at the first 3 or 4. Okay, this is some development that we have already done, and it was implemented in our skeleton ID software. Now, for the research part, we are looking at how to apply the likelihood ratio methodology to this kind of identification. So in our context, the evidence that we want to assess is the fact that a certain overlay has obtained a score value of, say, 5, or let's call it S for a generic score value. We are not dealing with a trial, we are dealing with identification, so the two sets of propositions are the following. First, the fact that the skull and the photo belongs to the same person, and the alternative proposition is that these two materials belong to different people. So if we review our likelihood ratio formula, now we have the probability of obtaining a certain score, given that skull and photo belong to the same person, and over the probability of obtaining the same score as, given that the material belongs to different person. So it's a little more complicated than before. Technically, well, we need to calculate the probability distribution of the score of the overlay when skull and the face belong to the same person in this case. So this can be measured experimentally, and luckily in the experimental study that I mentioned before, we did exactly that. We made a lot of skull face overlay, so we can just measure how many what are the score obtained by those automatic overlays, and we get this kind of histogram. Now we also need to compute the probability distribution when the skull and the face belong to different person. Again, we did it in the previous experiment, so we can get this other histogram. And once we put those two information together, we can see that in general, when we are dealing with the same person, so let's call it positive case, the score values tend to be quite lower than when we are mixing a skull from one person and a picture from another. This is good. We can also see there is some overlap between the two, which is to be expected because this score is not perfect, but at least in general, we know that we get smaller results in one case and bigger results in some other case. So now let's finally compute some likelihood ratio value. For instance, let's start with 8, which correspond to this horizontal line. And we can see that the probability of scoring 8 when we are dealing with an overlay of the same person is almost 20%, while with different materials, this is just 0.3%, which gave us a large likelihood ratio value. If we go to a score value, which is more in the overlap between the two, we get roughly the same number. So the likelihood ratio value is almost 2. And finally, when we go to a very high score value, we get that the probability of this being a superimposition involving the correct candidate is very low, and the probability of this being an overlay from with different materials is very high. And indeed, we get a very low likelihood ratio number. So Empirically, we have shown that high likelihood ratio values are associated with identification, and low likelihood ratio value correspond to exclusion, which is the perfect, well, it was our desired result. To test this in a more precise way, well, we determined that we can put two thresholds on the likelihood ratio value. In particular, whenever the likelihood ratio is higher than 115, we can conclude that we are dealing with the same person proposition, and this is correct 99.5% of the cases. And for the opposite conclusion, when the likelihood ratio value are very low, below 0.01, we are dealing with different materials in the 99.1% of the cases. Okay, so thank you very much. That's the end of my talk.
I will be quite briefly, and I want to show you how we are planning to somehow integrate all these maths into our software. So, well, some of you already know me or Andrea. We're working at the University of Granada for a long time, and now at Panacea. Well, we are working for many years in the automation of different identification methods and the development of decision support tools. And as you see, this automation will allow us to apply likelihood rating, as explained by Andrea, so we can provide a statistical support of a given evidence. And in this sense, what we are talking now is in forensic anthropology. That's in the field we are working, we are focusing. So all the technology we are developing is published, so you can see many papers in different journals, artificial intelligence journals, anthropology or forensic medicine journals. And in this sense, we plan to also submit this work, Andrea has just explained it, to a journal in a short time. But in addition to developing technology and sharing our achievements with the scientific community, we develop software as well, where we integrate all these algorithms. And this software is Skeleton ID. So just give me the chance to briefly explain a couple of things and share my screen. So Skeleton ID is composed, Skeleton ID is composed of what we call the core, which includes, the management of the institutions, the user, antemortem and postmortem databases, etc. It also includes what we call the virtual lab, which is a graphic engine that allows us to work with 2D and 3D images, of photographs, medical images, scans of different bones, and offers a multitude of tools to apply different identification methods. But at the same time, we have what we call the modules, which makes Skeleton ID a tool to support multiple purpose identification. So what you see there is some of these modules are already developed, others are under development, and others are in early stages of research, such as the facial phenotyping module. We are really on the first years of research. But each module groups artificial intelligence algorithms that automate different tasks of a given forensic anthropology method. For example, the craniofacial superimposition modules include an algorithm that automatically overlays skulls and face, as Andrea explained it. And in a couple of months, we will finish the integration of another different set of algorithms to automatically locate landmarks on the face and on the skull, and to estimate the pose and the subject to camera distance. So back to the topic, today's topic, likelihood ratio. Skeleton ID, we have, thanks to all this automation, the possibility to help on decision making especially in scenarios of multiples comparisons, what Andrea was referring as ranking of candidates. And I will show you right now how does it work. And once we are working in a, well, let me just briefly. So this is a skeleton ID interface.
Oscar, you might need to change your screen sharing. But we're still seeing.
Okay, you're right. Sorry. I forget to share the whole screen, no? The entire screen, sorry. Okay. No, sorry. Where? Okay. No. Okay, sorry. So I have just a few examples here. We have been working a few years ago with Rimantas Jankauskas and his team on a mass grave in Lithuania. So we have here the data. We have 11 antemortem cases and 22 postmortem cases. And what we are developing, and will be, as I said, in 1 or 2 months ready in skeleton ID, is this ranking possibility. So if we go for the list of antemortem cases and we select one of them, we can automatically get all the potential, a comparison with all the postmortem cases with a score. And this score is exactly what Andrea told you, no? Well, the number is different because it's a different mathematical function, but it's the same, no? And this will allow us also in a short time, because for a long time we are developing a large reliability study involving millions of cross comparisons. So at some point we can say what Andrea said at the end, no? With these 78 cases, we can say how to interpret a given score and to calculate likelihood ratio and say the probability associated with the evidence. So right now we have this order and we have the score, but we don't know to how many cases we have to look at. In the near future, we will be able to limit the search for just a few samples, and also integrate probabilities. And this can be done in any every technique. If we have an automated algorithm, we have a reliability study, a large reliability study about the score you are using, no? And another example would be in the field of dental comparison. We have here data provided by Chipi Kahana. I think Chipi is with us today. And she provided antemortem and postmortem odontograms of 128 cases. And we can do the same. We can select one case and look for the most, the better potential matches among the 128 postmortem cases. And we have a score. And this score, again, could go through this likelihood ratio methodology and support probabilities, so have a better decision-making process, more reliable, and more in the way that, as Andrea said, as the European Network of Forensic Science Institutes is already recommending to apply likelihood rating forensic science, and I think forensic identification, forensic anthropology will be also asked in the near future to provide this type of value. So that's why automation is also important. No, it saves time, it makes the process more objective, but at the same time, it also gives the possibility to calculate probabilities. And I think that's all from my side. I really thank you all to attend, and well, I guess is I don't know if Sebas want to say something or just leave.
I just wanted to want to leave people with one thing. If they want to try it, we have an email address they can just send an email to, just in case they want to try skeleton ID themselves. We arranged a tryout session